Hello! Hello, this is going to be one of hopefully quite a few videos where I'm going to talk you through the notes that you'd normally have in lessons to supplement your independent learning at what is, the time of recording, some very strange times with the coronavirus, need I mention. So I am aware that on Monday of the week just gone we did this chapter in class, Pure Chapter 12.1, but because of my slightly OCD nature, I feel I must start my recordings from the beginning of each chapter, so we're going to have a look at this chapter again, which can't hurt and will also benefit the people that weren't there on this crazy Monday just been. So the chapter's differentiation, and this will be following from the book which you have. And so afterwards I'm going to ask you to do some questions from the book like I would do in normal lessons. So first of all, as ever, let's have a look at the warm-up questions, which you can predict were coming, no doubt. And so have a go at these now. If you've not got the handout, check my Padlet and the emails I've sent you. If you can't access the Padlet, please have a go at just jotting down these questions and pause the video. When you're ready to see the answers, start the video and we'll talk through these solutions together. Okay, and here are the solutions coming up. So, question 1. Find the gradients of the following straight lines. So for 1 part A, we can just rearrange to y equals mx plus c. And so for 1 part A, we can just say that this is y equals 2x plus 4. Therefore, obviously the gradient is going to be 2. For part B, we get that y is going to be 3 over 2x minus 7 over 2. Now the constant term doesn't really matter, as you should know. The gradient is just given by the coefficient of the x term. So for part B, the gradient would just be 3 over 2. And for part C, slightly harder but not too bad, the function of x here is we're going to square whatever we're inputting into the function, then plus 2 lots of itself. And so if our input is not x but x plus 1, that means we're going to be squaring x plus 1 and then adding on 2 lots of itself, in other words 2 lots of x plus 1. So expand out these brackets as we should know how to do. We get x squared plus 2x plus 1 and then plus 2x plus 2. Finally, group together the terms and simplify. We should end up with x squared plus 4x plus 3. And so the answer to part C is just x squared plus 4x plus 3. Question 2. In each case, find the gradient of the line segment A to B. So quite simply, we just need to remember how we define the gradient. And the gradient between any two known points on a line is the change in y, delta y, all over delta x. And so with your calculator or otherwise, you need to work out the change in y from 1.21 to 1, and that's going to be 0.21. The change in x from 1 to 1.1 rather is 0.1. So 1 divided by the other yields 2.1. For B, same method, just different numbers. Now, if you have a look at these numbers here, I want you to just be thinking, how do the x and y coordinates relate? Now, for the first coordinates A, we can't really tell, but have a look at B. How do these relate? Because this is going to be key for this session. So you be pondering that as we do part B. For part B, the change in y is 1.0201 minus 1, which just gives us 0.0201. And the change in x is 0.01. You can see here my inability to write in a straight line hasn't disappeared, going downwards, but never mind. For B, gradient is 2.01. And for C, the gradient, change in y over change in x yet again. Only this time we have 0.002001 all over 1.001 minus 1, so all over 0.001, and that gives us 2.001. So we seem to be getting closer and closer to a gradient of 2. As I say, think of the difference between these points, 1.1 and the y coordinate, going forward each time. We're going to return to this in a moment. So have another think of this. In a moment I'm going to put the answer up in terms of what the relationship is. Okay, the relationship is, if this is x, this is x squared. And so the function we're talking about here, for example 2, is f of x being x squared, or y equals x squared. Question 3, expand the following brackets. So first of all, x plus h all squared. So for a, if we expand a binomial bracket to the power 2, the first term is just simply x squared. Then we double the product, so 2 lots of xh plus h squared. And for b, now if you wanted to, you could use the binomial expansion for this one. So either way around you do it, you should get x cubed plus 3 lots of x squared h plus 3 lots of x h squared, and finally plus h cubed. And for question 4, using the answer to 3 part A, find the gradient of the line segment AB, where A is x squared, and B is x plus h, brackets, x plus h all squared. Okay, so we can use the example from earlier. So yet again, just defining the gradient from first principles, the gradient of any line segment is the change in y between the 2 known points, divided by the change in x between those 2 known points. So in this case, it's going to be x plus h all squared minus x squared, and the change in x is going to be x plus h subtract x. And so expand this out as we did before. We have x squared plus 2xh plus h squared minus the x squared. And on the bottom of the fraction, what we're going to do is simply have remaining just for h. The x's will cancel. X and a minus x eliminate one another, so just left with h. In a similar way, if you look at the top, what's going to eliminate each other here? Can you spot it? It's going to be the x squareds, so they can go. And so we're just going to be left with 2xh plus h squared all over h. So we can divide both the terms in the numerator through by h, and we just would remain with 2x plus h. And so how does all this link into the bigger picture today? So we're going to explain and have a look at what we've been doing here in terms of the gradients. So the gradients of curves. So a few pictures, as you can hopefully see in your notes if you've been lucky enough to get them printed off, or if not, from the Padlet. The gradient of a curve is constantly changing if it isn't a straight line graph, as you can see in figure 1, the 3 different images below. And so a tangent tells you the gradient at any particular point on a curve. And so the tangent, as you can see, is just the slope at any one given point. So in terms of defining a tangent, you just need to be slightly careful. A misconception is that a tangent can only touch a curve once. That more or less explains it well enough in most circumstances, but just to be a bit clearer, a tangent to a curve at point A is the straight line that just touches the curve at A. Now, I don't mean just as in necessarily just once, but just scrapes it. So just touches it without going inside the curve. So if you have a look back at the previous one here, this tangent, for example, does cut the curve again, but only because the curve changes direction. And so this can cut the curve more than once, but it only just touches at any one given point. Now, a slightly better definition is the tangent at any point A can be thought of as the straight line through 2 points an equal infinitesimal distance either side of a point A, where infinitesimal just means so small it's too small to measure. And the gradient of a curve at point A is one and the same thing as the gradient of a tangent to the curve at that point A. Okay, this is one for you if you can. I want you to, using your notes, use a pencil and a ruler to estimate the gradient of the curve, in this case y equals x squared, at the point A, which is 1, 1, by drawing a tangent to the curve. Calculate your estimate in the box provided. In case you're not sure what I mean to do, what I mean is this. So I want you to get a ruler, draw in a tangent to the curve. I'm going to try here for you, using my tools on this board. So that will probably do me. Pick any 2 points on the curve, da-dum, da-dum, or whatever you want to pick. Work out the change in y, divide by the change in x for yours. Don't just copy me, try it yourself, and see what you get for your calculated gradient. So if you want to pause it now and try that. Okay, so let's compare notes. Let's see what you got compared to what I got. This is one I did earlier. For mine, I got that the gradient at A was 1.95, which you might have got similar to as well. So mine's pretty much 2. A couple more for you to try. Here, the same curve, just different points on the curve. The first one, I'm choosing x to be 1.5. Figure 4, I'm choosing at the point of x to be 0.5. So same process, please. If you can use your pen and pencil to construct a gradient at each point here for B and C, and don't work out the equation of a gradient, just simply the gradient of that tangent, and see if yours compared to mine in a similar way. So I'll just give you a few seconds now if you want to pause and then try that. Okay, let's have a look. For figure 3, I got a gradient of exactly 3, and for figure 4, where x was 0.5, I got a gradient of 0.97. So can you use these results to postulate, which is a fancy word for guess or predict based on previous evidence? Can you predict what the gradient of a curve y equals x squared is for any general point on the curve x and y? Okay, be thinking of it. I'll give you a hint if not. Try and compare the value of a tangent for each point to the x-coordinate of each point. Okay, so maybe pause the video and have a think about that. Okay, well here is what I'd be considering. When x was 2, my apologies, when x was 1, the gradient was near as damn it 2. I got 1.97, so for the nearest whole number it was 2. When we picked x as being 1.5, we saw the gradient was very close to being 3. And the last one for figure 4, when x was 0.5, I got that the gradient was fairly close to being 1. Hopefully you got something similar, at least to the nearest whole number. I'm hoping you did. And so what's the relationship between the x-coordinate on the curve y equals x squared and the gradient at that point on the curve? 1 goes to 2, 1.5 goes to 3. When x is 0.5, it goes to 1. Hopefully you can see that the gradient for any point xy on the curve y equals x squared, the gradient is simply double the x-coordinate. And so the gradient in fact, no, I'll say the gradient at x, y for the function y equals x squared is 2x. So that's quite rough and ready, maybe not entirely convincing yet, but I'm going to try and convince you and show you why that is the case. So let's move forward. So let's try and define this more robustly. We've got here a sketch of y equals x squared, and I want you to imagine a general point A on the curve, where A is just given as x, y. Now y is going to be x squared. What we're going to do, and I want you to do this as well on yours, is to define a second point on this curve, B, where B is x plus h, and x plus h all squared, where h is a fairly small constant. And we're going to see what happens when h changes. So we're going to consider the gradient of AB when h becomes really small. So here's my first B, And this green line represents the line through A and B. And so the steepness of the green line is the gradient of AB, whereas the red line will remain unchanged. That's the gradient of a tangent. It's the gradient at the point A. So let's see what happens when B gets closer and closer to A, when H shrinks down smaller and smaller and smaller until it gets close to 0. So I'm just going to click through. Here, the green line's above the red line. This one's steeper, but as B moves closer and closer, as H decreases, you can see it's getting closer, 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 and closer again to the red line. And so hopefully you can see in the absolute limiting case where B would become on top of A, as H shrinks down to 0, the gradient of a green line becomes a gradient of a red line. The gradient of AB becomes the same as the gradient of a tangent, and that's going to be a powerful result which we're going to use. Now that's just one curve, y equals x squared. I'm going to try and convince you that that's the case for all curves. So here's a different one I found earlier. So looking at this animation, we can hopefully see that it works for any curve. This is a different quadratic. Instead of AB, this is P and Q. The blue line is the tangent. Look what happens when Q gets closer to P. The red line becomes the same as the blue line. So the gradient of a tangent is the same as the gradient PQ when Q becomes P, when H shrinks down to 0. And so we're going to consider this now. So as H becomes smaller and smaller, close to 0, the gradient becomes equal to the tangent. So let's see algebraically how this is going to work. Okay, so we can write it as such. So the gradient of a tangent, in other words, the gradient at A. Now we write this in terms of A and B. It's the limit when H becomes 0. That's the technical way of writing it. LIM for limit. H arrow 0 means the limit as H gets closer and closer to 0. It's the limit of the gradient AB. Now this can get quite tedious to write, so never mind that. So it's the limit as H gets close to 0 of a gradient A to B. So that's a change in Y divided by the change in X. So let's just define this now. Y at B is x plus H all squared. Y at A is just going to be x squared. Meanwhile, the x-coordinate of B is just x plus H. The x-coordinate at A is simply x. Now the denominator we're just left with H. That's going to be a common theme we're going to see again and again. So let's just neaten this up slightly. So that's the same as the limit of H going towards 0. So let's neaten up the top of this fraction. We have x squared plus 2xh plus h squared minus x squared all over h. Again, this expansion here was what we did in the warm-up question, so hopefully you can see this link and the relevance to that. The x squareds will cancel. So you need to be writing this down with me in your notes if you can do, obviously. So we're going to be left with, on the top, 2xh plus h squared, and we can cancel through all this by dividing through by the h on the denominator. And so we get the limit as h goes towards 0. 2xh divided by h is just 2x. H squared divided by h is h. And so what's going to happen when h shrinks down to 0? 2x doesn't depend on h, and so 2x is just going to be 2x all day long, but h will shrink and vanish. And so the absolute limit of the gradient at the point xy is going to be 2x. So therefore the gradient of the curve y equals x squared is going to be 2x for any point on the curve. So for example, when x is 5, the gradient of a graph y equals x squared would be 10. And that proves our results from earlier. This process here is called differentiating from first principles. There is a quicker pattern we will discover and use in other lessons, but for now we're going to be practicing this powerful method. This is very common in exam questions, and so it needs to be known and understood clearly. So, a bit more definition and notation. The gradient function is called the derivative, and it's written as f dashed x or dy by dx. And so, for example, for y equals x squared, we could write dy by dx of x squared, or even d by dx of x squared, equals 2x. Or even f dashed of x squared is 2x. And it's always going to be the limit as h goes towards 0, the change in y minus the change in y at the top, the change in x just becomes h. So it's always y2 minus y1 all over h. That's the general pattern we can use time and time again. And so, as I've said, using this method to find the gradients of different curves is called differentiating from first principles. So let's try a few examples. Okay, work with example 1. From first principles, prove that the derivative, the gradient of f of 5x is 5. Okay, I'm going to do this one with you. I'm going to suggest for the next one you try it yourself after pausing the video. So for this one, we want to define our function of x. So this time our function of x is 5x. Now from earlier on the slide I just showed you, f dashed of x, the gradient function, is the limit as h goes towards 0 of f of x plus h minus f of x all over h. Okay, now we defined the function of x to be 5x. So the function of x plus h is just going to be 5 lots of x plus h this time. So 5 lots of x plus h minus 5x all over h. So let's expand this out. I'm just going to put limit as x goes towards 0. That would be wrong. It's as h goes towards 0. So we have 5x plus 5h minus 5x all over h. And so on the top, what's going to happen is 5x minus 5x, they'll both cancel each other off, and we'll just be left with 5h divided by h, which just gives us 5. So the limit as h shrinks down to 0 of 5, well 5 is a constant. By its nature, 5 is just 5. It's just 5, so h can do whatever it likes. It's not going to change the fact that 5 is 5. So that just equals 5. So therefore, the gradient function of 5x, f dashed 5x just equals 5. Okay, and that's what you probably already knew. If you've got a graph of y equals 5x, just using the idea of y equals mx plus c, the gradient is just the coefficient of x, which is 5. So it's obvious you should know this, but this proves it very robustly. The gradient function of 5x is 5. Let's try a slightly harder one. Prove from first principles that the derivative of 3x squared is 6x. What I'd suggest you do is you try this one yourselves, pause the video now, and then play it and see if your answer reflects mine. Okay, well here we go. So, split my screen in two. So again, let's use the same first principles. The gradient function is going to be the limit as h goes towards 0 of f(x plus h) minus f of x all over h. Okay, so let's write that again. Lim h goes towards 0. So we're going to say here, if the graph is 3x squared, then we can say our function of x is 3x squared. Always nice to define it in that way if we can do, which we can. So if our input, we just simply square it and then multiply it by 3. If our input now is x plus h, then f of x plus h will be 3 lots of x plus h all squared, minus f of x, which is minus 3x squared, all over h again. Hopefully you can see now what we're doing, what the game is. So expand this out and remember to multiply by the constant term 3 at the beginning. So x plus h all squared would begin with x squared. So multiply that by 3, we'd have 3x squared. The next term would be 6xh, then plus h squared, bit of a dodgy h there, minus 3x squared all over h. Again, come on, spot for me. What cancels on the top? You tell me, before I tell you. Shout at the screen if you want, but not too loud so it disturbs your parents or whatever. Okay, 3x squared cancels, doesn't it? There you go, bye-bye. So now we just have 6xh plus h squared all over h. Again, you can see here what's going to cancel. There's a h in each term on the numerator, so we can cancel those off. So it's the limit as h goes towards 0 of 6x plus h. So as h goes closer to 0, the h is just going to vanish altogether. So we're just going to be left with 6x. Therefore, the gradient function of 3x squared is just 6x. And the last one, before I want you to try some questions on your own, is to prove from first principles that the derivative of x cubed is 3x squared. So again, here we can define the function of x as being x cubed. Pause the screen and try it yourself, that's what I'd like you to do, and then play when you want to compare your answer to mine. Okay, here goes. So again, define the function, the gradient function, as the limit as h goes towards 0 of the change from f of x plus h from f of x, all divided by h. So now we just substitute in what f of x plus h would be. So this one would just be x plus h all cubed. And again, we can use the notes from the start to help us with this one. Minus f of x all over h. Gosh, my hand's getting tired. Never mind. So x plus h all expanded out would give us x cubed plus 3 lots of x squared h plus 3 lots of x h squared plus h cubed, and finally minus x cubed. All of that is going to be divided through by h. Again, look for any cancellations if and where you can. Here, the x cubes will cancel at the beginning and end, and so we're going to be left with, on the top, just going to have 3 x squared h plus 3 x h squared plus h cubed, all of which gets divided by h. So if we just divide through all these terms by h, which we can because they all have a h in them, we can cancel off these h's. We just have 3x squared plus 3x h plus h squared. Now just imagine the effect as h goes towards 0 of the term 3xh. That'll become 3x multiplied by nothing, which will just vanish, and h squared will become close and close to 0 squared, which will become basically nothing. And so we'll just be left with 3x squared. Hence, the gradient function of x cubed equals 3x squared. Whoops-a-daisy, that's badly written. Apologies. Give myself a slap on the wrist when this video is done, don't you worry. So f dashed of x cubed is 3x squared. Okie doke. Now, what I want you to do as well, before we do the next lesson, I want you to just reflect on these results. I'm not going to tell you now what they are. When we had f of x as x cubed, the gradient function was 3x squared. Going back one, when our function was 3x squared, the general gradient at any one point was 6x. Is there a pattern here? And the gradient function of 5x was 5. I'll give you one clue. Think about the power of x each time. So 5x, gradient becomes 5. 3x squared, it became 6x. X cubed became 3x squared. Just have a think of that. If you get it before the next lesson, great. If you can discover it yourself, it's that more powerful. Okie doke. So now, using your lovely Edexcel Pearson books, I'd like you to turn to page 261 to 262, exercise 12b. Try questions 5, 6 and 7, and then the challenge if you're brave enough. Thanks very much for listening. I hope this wasn't too bad. I'll see you again next time, and feel free to leave me any comments in the comments section. Okay, see you soon hopefully, and take care.